Hello and welcome to another session of EPO 640 electric drive lecture. So for today, we will be discussing on the last chapter of our semester. That is the other types of drive. So this will be part 1, and we have other types of drive part 2. Okay, so for other types of drive, we will look into switch reluctant drives. Okay, so switch reluctant drive was derived at Nottingham and Leeds universities in the late 1970s and on the early 1980s. Okay, and it's used for electric transport. But it was commercially available since 1986, and it have recently been used in high-end domestic products. Okay, for example, you all know the Dyson washing machine and vacuum cleaners. Okay, so they have been using switch reluctant drives, and also on blade hand dryers. Okay, and the power range of the switch reluctance is around 100 watts to 250 kilowatts. Okay, so it can be very big. So the drive basics, okay, it works on the principle of a magnetic attraction. Okay, so it's independent of the direction of the field. Okay, and it uses a winding which only requires switched DC, okay, instead of an AC. Okay, and for this it uses fewer power electronic switches, and the rotor, it does not have current flowing to the rotor. So there is no connection required to the rotor, and you only require a cooling on the stator. Okay, so let's look at the drive principle. Okay, so as you know, the MMF, electromagnetic force, okay, is equals to the value of flux. Okay, of course, flux times the value of the reluctance. Okay, so in a magnetic circuit made up of an iron, okay, so you have your rotor that is made up of an iron, and also between the rotor and the stator you have air gaps. Okay, so the reluctance is almost entirely okay, the reluctance that is produced is because of the air gap. Okay, is entirely due to the air gap. Okay, and if a part of the magnetic circuit is movable, okay, so if an MMF is applied, okay, to it, it always moves to the minimum reluctance position. Okay, so of course, in theory of electricity, okay, current flows, okay, will choose the less resistance or less reluctance flow. So it's the same with MMF. So if it's a magnetic circuit, so for magnetic circuit, flux will always choose the least reluctance path. Okay, so for the switch reluctance motor, you have your rotor, okay, which is for this example is iron. So the maximum reluctance will have less air gap. Okay, so if the rotor is positioned upwards like this, okay, so you have a least amount of air gap, which is the position of the most minimum reluctance. Okay, and if you have your rotor in this position, in this diagonal position here, So you can see that you have more air gap created, okay, in this position. So this will be the maximum reluctance position for the motor, okay, and this will reduce the value of MMF, which is in a magnetic circuit. So this will be the least value of MMF. Okay, and if you take the overall picture here, so you can see that since the motor, okay, so you have the force. If you look into the MMF will create force. So the force will turn the rotor, and that will give the value of the maximum and minimum value of MMF, and also the maximum and minimum value of the reluctance. Okay, so the coil, the winding will energize the iron stator. So the iron stator will create the magnetic circuit. Okay, so magnetic circuit will flow in this direction. Okay, for example. Okay, and here you can see the phase inductance. Okay, phase inductance within the rotor to the stator to the rotor. Okay, so you have your inductance is maximum. Okay, in the position. Okay, A B A and B. Okay, so you have the least reluctance here. So you have the maximum inductance value, okay, phase inductance value during this position A, and then B, and then it will slightly reduce, okay, the value of inductance, okay, and when it reach the D position, which is the rotor is diagonal, okay, in position, so you have the least value of inductance, okay, L minimum, okay, and you can see the reluctance is high, okay, during this, okay, and the rotor will turn, okay, and it will if you okay, measure the value of phase inductance, so you can see trapezoidal condition here. But when you measure this is on simulation, but if you measure on a actual motor, so you can see the graph will be more sinusoidal. Okay. So if current is switched into the windings when the rotor is at the position of maximum reluctance, okay, so torque will be developed, okay, to pull the rotor to the position of minimum reluctance. Okay, and the apparent inductance of the winding will vary within the rotor position, and this can be approximated by the inductance profile. Okay, so yeah, this is what I call it oversimplification. So in a more realistic experiment or measurement, so it will be more sinusoidal. Okay. Okay, so you can see that later on we will discuss on the phase and the phase current and the torque. Okay. And the equivalent circuit, okay, you can see the equivalent circuit, how we develop the equivalent circuit. So so you have the inductance is it's a function of the rotor position, theta. So so inductance, we can say that in L equals to L theta. Okay, so we want to make it we want to derive, okay, so that the inductance, we can say that inductance is the function of the position, rotor position. So voltage, okay, voltage equation, okay, we know that to get the value of voltage, okay, is the derivation of, okay, L times I, okay, V equals to I d over dt L, okay, and it's because of the role of the change of flux in the linkage, okay. So this will be the voltage, okay. So when we separate for both di and dl, il, okay. And if we want to calculate the power, so V times I, so you get this equation, okay. And also P is also equivalent to P mechanical, okay, plus the rate of change of the stored magnetic energy, or we call it P mech, and P mech is this equation, okay, d over dt half, okay, half times L times I power to 2, okay, and we will get this equation, P mech. So what is P mechanical? Okay, so P mechanical is P in minus P mech, okay, and you can see that if we differentiate the position, you'll get the speed, okay, and this is the speed of the rotor, and we can also calculate TE, the torque, okay. So torque is P mechanical over speed in radian, omega r, okay. So you get this value, okay. This is the value of torque. So the torque is independent, okay. From here we can say that the torque is independent of the current direction, okay, and this can be simplified the power electronic design, okay. So another thing that is the torque is very dependent on the rotor position, okay. So a shaft mounted rotor position sensor is very important for you, okay. So from this information here, we can draw our equivalent circuit, okay. So it's just a simple, okay, you have your input, okay, you have your L, and you have your your power here, okay. So this is when this is for P mech, and this is for back EMF, okay. So the back EMF, okay, when we multiply with I, we'll get the mechanical output power, okay. So this will be the P magnetization, magnetization, and the P mechanical power, okay. So this part plus this part equals to P input, okay. So we are following the this equation, okay. So this is the equivalent circuit of the this is the equivalent circuit of the switch inductance motor, okay. So further analysis you have, okay, so for example for motoring, okay, during motoring from theta 1 to theta 2, okay. So to calculate the Lmax, okay, Lmax minus Lmin, so you have your dl over d theta, okay. So here you have your peak torque, okay. So for this equation, and this will be the mean torque. So during this is okay, so the what call it, the differentiate, okay. So the movement from the value of inductance from minimum to maximum will create this torque, the torque value is peak torque, so this is during motoring, and of course in the opposite, okay. So during you have your maximum to minimum when it's moving from maximum to minimum, so this is during for generation, So dl over d theta is negative when coil is energized. Okay, and so you have your peak torque is now negative, and this will be the mean, okay, mean torque value. But in reality, it's not easy. Okay, what you call it? It's not straightforward. So in reality, the phase inductance is more to mimic the sinusoidal. Okay, so so this what you call it? This equation will be used. Okay, this equation to be used to calculate the torque. Okay, so there are two basic modes of operation of the switch reluctance motor. The operation mode depends on the rotational speed. Okay, so both modes aim to control current in the winding, as this direction controls the torque in the machine. Okay, so at low speed, the aim is to control the amplitude of the current in the winding during the period of increasing inductance. And at high speed, the aim is to maximize the mean current during the period of rising inductance, and this is achieved by the timing of the position and the width of the current pulses. So at low speeds, the current builds up very quickly in the winding. Okay, so when a voltage is applied, and this is mainly because of the back EMF, okay, is low. Okay, and the phase current must therefore be controlled by chopping. Okay, so yeah, there is some extra, what you call it, extra process that you need to do for on the controller for low speed. Speed. So this is the control during the low speed. So you have this choppy, the phase current. So phase current is some sort of what you call it, choppy, and so this will affect the rotor position also lah, the motor torque. And as the speed increases, so the numbers of chops reduces, and it becomes better. Okay, so it's better to use just one pulse. Okay, so at higher speeds, the current builds up more slowly. Okay, so because the term is the I times speed times dl over dt term is much higher, resulting in a lower net voltage. Okay, and for causing the winding current to change. So the time corresponding to the region of positive dl over d theta is much shorter, and there is now only time for a short current pulse. So in order to maximize the mean current, okay, during the pulse, the switch on edge is advanced by an angle, okay, or theta on. So it's to ensure that there is a suitable high current as the motor enters a positive region. But however, there must be no current in the winding. Okay, when the L over the d theta is negative, it's to prevent the negative torque. Okay, so therefore the switch off edge must also be modified. Okay, so you can see here. Okay, so it's a much smooth operation. Okay, but then we need to be careful on the negative dl over d theta. And the angles must be adjusted. So the adjustment angles, okay, on the theta of are speed dependent. As the speed increases, this angle must be increased further. Okay, and at lower speeds, these angles are reduced. Okay, so in practice, there is a map of theta on and theta off against speed for all desired torque values. And many combinations of theta on and theta off can give the same torque. And the combination for maximum efficiency is usually chosen. So the possible power circuit that can be used is a simple. This will be the half bridge design. So you have your Q1, Q1, Q2, and so this will be the possible power circuit, and so for the drives, so it needs continuous production of torque. So motor starts from, it can start from any position. So the recovery of stored energy from winding is at turn off, and the control scheme for all speeds, and therefore it needs more phases. So for example, for a 3-phase 8 to 4 ratio motor, so 8 stator to 4 rotor motor. So it excites phase A, then phase B, then phase C, and so on. So the motor spins anti-clockwise, following the stator field, and thus the rotor will go in the opposite direction. And for a 3-phase system, so this is an example of a 3-phase system. So you have your bus here, and then switch will be the switch will be turned on and off according to the position of the rotor. So advantage of this switch reluctance drive. So for this example, a rotor and the impeller from a switch reluctance based vacuum. So in this case, you have you can connect directly the impeller to the rotor, and you don't need gears or any extension that can reduce the efficiency of the drive. So in this case, a rotor or the commutator and the impeller from the conventional vacuum cleaner. So you can see that so for a switch reluctance based vacuum cleaner, but this case they don't use gears and so on. But you can see that you don't need all this additional windings on the rotor part. So you can see this is just an iron stick here. So this, you can see it's very troublesome, and the design is quite complicated. So this is conventional, and this is switch reluctance based. So other advantages, for example, you have all power losses. All power losses is at the stator, so there is no current in the rotor, and thus it makes the cooling very easy and gives high power, power to size ratio. And the rotor has a very low inertia, and has a good torque inertia ratio, and this gives a rapid speed response for high performance drive, and each current pulse is a separate event. So therefore it can go from maximum positive torque to maximum negative torque in a very fast response, in a consecutive pulse. And so if you can see the less components in the rotor, so it makes it simple, and thus it makes it a robust motor. So you can check out on other on your other textbooks or other sources, in SR drives, switch reluctance drives. So for that, thank you and have a nice day.